Hey. Morning, everybody. So it is my pleasure to introduce Grigorios Tsoumakas from the Aristotle University of Thessaloniki, and his work focuses, he has worked on machine learning and NLP for already 2 decades, at least, maybe longer, and received awards from his work, like Best Paper Awards, the Test of Time Awards from machine learning conferences. And today we have the pleasure of hearing him tell us about the neural abstractive summarization methods and applications, the work that he has done at the university and also at the company Medoid AI that he has founded. So please, Greg.
Yes, so hi everyone, and thank you, Beck, for the kind introduction. I'm really excited to be here to talk to you about our work on neural summarization that we have been doing the last, I would say, 5 years or so. So I will first introduce a little bit the task and some of the models we are using. Then I will talk about our work on Bayesian active summarization, so trying to make the most out of a limited budget for annotated documents. Then our work on how to control the output of a summarization model towards some features like, in particular, the topic to make it more personalized. And I will continue with some applications in the healthcare and finance sectors. And if we have time, I might also discuss with you one of our first works on this. That's about how to deal with long documents. So let's start. So we are, as you know, all living in the era of information overload. In 2025, it is predicted that we will have 175 zettabytes of data. Much of this data is text, like emails, posts in social media, academic articles, more than 1 million only in healthcare articles are written each year. And automated summarization can help us with this information overload. They can, of course, reduce the reading time for humans, but they can also reduce the cost and bias of human summarizers. And they can also help with downstream tasks like indexing documents. And of course, we see the large interest of enterprises like Google and Meta that are using this technology in their services. So there are two main categories, extractive and abstractive summarization. So in the middle column, you see an article that is more than 2 years ago discussing what agenda of the United Nations General Assembly. Unfortunately, it's the same topics today, like the Russia's invasion of Ukraine and the climate change. And you can see on the left an extractive summary. So this type of summary copies verbatim text from the input document, and these are the blue text in the middle. While on the right, you see an abstractive summary that tries to, let's say it in the model in its own words. And you can see that it has copied some text, but it has also created some new words like paraphrasing, dominating and abbreviating United Nations SUN. So we will focus in this talk on the abstractive type of summarization because I believe it's also closer to how humans try to summarize a document, and it's more interesting. The models that we will be discussing follow this encoder-decoder architecture of the transformer as it was originally proposed for machine translation. Nowadays, of course, large LLMs typically use only a decoder and prime the decoder with the input and instructions on how to process the document. But as I said, we focus on this more traditional and lighter, let's say, architecture. But despite being lighter, it still needs a lot of data to train the millions of parameters around here. So we typically don't train these models from scratch, but we use pre-trained models that have been trained in huge amounts of data, and then we fine-tune these models to a particular use case, domain, scenario, etc. So I will show you two models that you will be seeing later on in the introduction. The first one is Pegasus. It has 16 layers and about 500,000 parameters. It has been trained on terabytes of data, mainly news, but also web pages. And the way it has been trained is with this gap sentence generation objective, where a percentage, typically around 30% of an input document, is removed from the document, and the union of these sentences are the target that the model has to predict. So here, in this example, we have three sentences. Pegasus is mythical, it is pure white, it names the model. The middle sentence is must and used as target to the decoder. You can also see some traditional masking of words as done in the BERT model, for example. But this doesn't really help in the performance of the model. But what is important is the removal of whole sentences. So this is a model from Google, and another quite interesting and successful model is BAR. So this one has a few less parameters, around 400 million, less layers. It has been trained also on less data news, but also web and books. And here the objective is basically it acts like a denoising autoencoder. So we have corruptions of the original input text in the input, and you can see some types of corruptions like permutation, document rotation, token deletion, etc. And the model has to reconstruct the correct input from the corrupted input. So let's start with our first line of work on active summarization. So as we said, deep learning models are quite, as you know, data hungry. And it's not easy to collect high quality training data. And this particularly for summarization, for example, where someone has to write really a concise summary of an input document that contains the main elements being discussed without repetitions. And if we go into particular domains like the health domain or the legal domain or the financial domain, then you need to have experts, for example, medical writers in medicine. And this and their effort and work is more expensive. Perhaps you know from machine learning the area of active learning that helps us deal with this when we have a limited budget to make the most out of it. So we have a human in the middle that annotates data, but the main idea is to focus on samples where the model is uncertain about these samples, and we suppose that this will help more the model. So when we started working on this topic, there was no work on neural summarization, on active neural summarization. There was some old work on classical summarization with traditional techniques without neural models. So we published last year our work called BAS, Bayesian Active Summarization of Computer Speech and Language Journal, author 7. So you see here that we have these models that we were discussing. We have a set of labeled data, a large set of unlabeled data. And let's say we have a budget of 900 examples. Originally, we have 0 training documents. So what happens is that first, we need to keep apart some of the documents for validation, because you know that in order to fine-tune these pre-trained models, you have to set hyperparameters, so you need to have some validation data to be able to tune them. So we spent some of the budget for this. Then we also randomly, we select randomly this data. Also, we randomly select, spend a little more of our budget here, 50 examples, to warm up the model. Because initially, the pre-trained model doesn't have any idea of the particular domain we are working on, and it will not perform well and assess the we cannot assess its uncertainty well in terms of this particular domain we are fine-tuning. So we give it 50 documents to warm up, we train it, and then once we train it, now we can do uncertainty estimation on the large pool of unlabeled documents, and as per the principles of active learning, select the most uncertain documents, let's say 10. So we now drop to 74, and we repeat this process for 10 documents. Each time we take these 10 documents, we fine-tune the pre-trained model from scratch, so from its original pre-trained state, with the additional documents, and we repeat this process. Okay, so the crucial step here is how to do this, how to do the uncertainty estimation step. So one standard way to do this in deep learning is through Monte Carlo dropout, where we train our model with dropout, and during inference, we make multiple stochastic inference passes. So we do the inference with different dropout masks, and then we can measure the variance of the output, and this is an estimate of the uncertainty of the model. So, inspired by ideas in machine translation on how to measure the uncertainty in machine translation, we published in the findings of ACL conference 2 years ago this concept of basically running the transformer model for multiple times and getting multiple summaries, and then we need to assess the uncertainty of the model based on a set of summaries. We take this squared complement of the blue metric among all pairs of, let's say, the 10 summaries that we produced with the multiple runs. And blue is basically a metric that measures the similarity of two documents based on word overlap, engram overlap, things like that. So by this normalized version of its variance, we use it as a scoring metric to assess the uncertainty of our model in its unlabeled document. However, there is a problem with that, because this set of unlabeled documents is typically quite large. So in our experiments with XSUM, the XSUM dataset, this has 200,000 documents. So doing this multiple inference step for 200,000 documents is really doesn't scale. So we need to find another solution to this. And the solution is to do some sampling. So we sample a subset of these documents. So for, let's say, for example, 100, and then we do the uncertainty estimation of this on this smaller sample. And then finally, we add this the most uncertain document. And we continue this process before until we spend all our budget on this extra document. So this is the basic idea, and some results on the XSUM dataset. It is a dataset, a large dataset, as I said, with news articles from BBC covering a wide variety of topics. The first line, the columns are the Rouge metrics. If you are in the field, maybe you know them, they are popular. Again, they measure the quality of the produced summary with the ground truth summary based on the overlap of engrams. So we have rows 1, rows 2, and rows least common subsequent result. And if we see the first line is just the pre-training model. And as you see, because it doesn't have any knowledge of the particular domain, it doesn't do really well. The last line is the results, contains the results of the Pegasus if it is trained on the full 200,000 training examples. And it reaches, okay, some not exciting, but not bad also performance. Then we have this set of 3 lines where we have bus with a budget of 150 examples, the first, second to fourth line, and from lines 5 to 7 with a budget of 800 examples. And we compare what happens if we randomly choose the examples and if we use it through the strategy that we discussed with bus. And the last number shows how many samples, how many examples we sampled from their label data. So we see that bus improves over random. It's not an exciting improvement, and also random with so few examples already starts to become quite close to the full data set. But it's still if one wants to make better of its budget, to exploit better its budget, their budget, they can use this approach. And here we see the learning curve of bus with 100 samples and for a budget of 800 examples. And we see that it is more or less consistently above the random learning curve. One reason why BAS doesn't do that well, and all uncertainty estimation techniques basically, is because the uncertainty estimation leads to the selection of outliers. So there was a paper a little bit published after ours that proposed an approach where we select the samples to annotate only based on distances. So no uncertainty at all. And the idea is to score the samples based on the similarity to the unlabeled set we have. So try to focus on the distribution as a whole, but also select samples away from the samples we have already labeled. So try to explore different samples, but following the main distribution of the data. So here, for example, the red points are the ones already selected, and this IDDS approach would select the blue ones that are far from the red, but still they are close to the distribution of the data. And indeed, as they say, uncertainty-based methods select outliers. Also, BAS selected outliers, and we set a threshold in a heuristic way to avoid selecting samples with very high uncertainty, because this is like selecting outliers. So based on this paper, our work in progress now, that we hope to complete writing the paper within this month, is to try and exploit the best of all these different worlds. So here we see a comparison of BAS, IDDS, and a simple random strategy to select random examples. And what we see is that IDDS focuses in particular areas of the data to the way it works. And here actually it focuses also in between these two sub-distributions. BAS selects more diverse examples, but also select outliers. So there are some samples outside of the distribution. Of course, here this is like a 2D projection of data, but we can get some intuition. While random doesn't select outliers. So the idea is to try to combine these two, because often random sampling outperforms in some cases both approaches. So we thought to combine these two in this simple way, use IDDS to select a first larger set of representative examples, and then apply BAS to select a subset of this that have the higher uncertainty, but also include a component of random sampling that adds robustness to the whole process. And some initial results on this, here we see learning curves on two datasets, RediT and Bayesian, and we also have included an additional model. This is another text-to-text transformer from Google. Plan is a version that has been also trained with supervised data. And we see that the curve of dual, which is the red curve, in all of the datasets, apart from this, is consistently above both IDBS. And here, this plots show in 4 datasets, compare the diversity score and the applier score of dual, which is this red match. And we see that it stands in between IDBS and random in terms of diversity, so it's more diverse than this is IDBS, this is dual. It's more diverse than dual, and it is less susceptible to outliers compared to mass. So we hope to complete this work soon and submit it for publication. The next topic is about controlling the topic of the output summary. Sorry, how much time we have?
Maybe 15 minutes. 15. A little bit of time in the end for questions.
15 minutes, okay. So controllable summarization is a summarization where we want to control the output, maybe enforce the model to include named entities, adjust the length, adjust the style. In our work, we focus on adjusting the topic. So there were some related work when we started looking on this, like trying to add quote-encoded topic vectors to the embeddings of its token, or trying to incorporate topical information into the attention mechanism of encoded decoder RNNs. But these were proposed for RNNs, and we need to change the architecture to apply them to transformers. We wanted to do this with transformers. It's not clear how to do it. And also, the evaluation in these models work based on traditional rules metrics, and they don't capture exactly if the model essentially managed to reflect the topic that it was given to the results. So we have 3 methods for transformers that we proposed in this paper earlier this year in LREC calling. And we also propose a new evaluation measure, and all this require a kind of representation of the topic. So we assume we have a closed set of particular topics, and we have a set of documents for this topic. And for simplicity, we could use, of course, transformers to encode in a dimensional vector the documents and the topics, but for simplicity, we just use TF-IDF. So basically, for example, the representation for a topic like sports is just the average TF-IDF representation of the documents of this topic. Okay. And how we evaluate the results to see if the summary reflected the topic or not is that we take this, as we said, we have the TF-IDF representation for a particular topic. We compute the same representation for a particular summary that the model gave us, and we just consider the cosine similarity of these 2 representations, but we normalize it with the maximum similarity across the topic. So basically, if the summary is most similar to, if the topic is the most similar topic of among all the topics to the particular produced summary, then it gets a score of 1. And the rest are between 0 and 1. Concerning the 3 methods, one idea inspired from the work that proposed to include token embeddings and concatenate this with the standard embeddings. We use instead trainable topic embeddings that we add to the traditional word embeddings and positional encoding, because we cannot concatenate new vectors in the existing architecture. This would require an architectural change. So this is a simpler approach that can fit. Then inspired from control sum, that is a famous approach for controlling the output of models with respect to entities, basically, mainly. The idea is to just prevent during training the topic in the input summary. So if you have an input summary, if you have an input document and you have a summary related to politics, you give this in front of the input document. If you have for another topic, as you will see, you just put another topic. So very simple idea. It's like prompting, let's say, the model to understand that we want to use this topic. And our new idea is typing. So what we do is we consider the topic vector and we see which words are more similar to this, which words have the highest TF-IDF score in the topic representation, in the representation of the particular topic. And we put a special token, let's say tag, in front of these words. So here for politics, the word political and organization are more related to this topic. That's why we tag these words. But for the same documents, if we had a ground truth or we wanted to influence the model to produce a summary, for example, for sports, then we would put sports in the beginning during inference, but also during training, so that the model learns these associations. And here we see that we tag different words like NBA championship and games. So there was a lack of ground truth data with same document, different summaries at the point of time we were working with data. The solution is to just mix different input documents, as you see here. So the blue document is is related to sports, but the purple one is related with energy and environment. So we mix these documents, and we have one training example with one of the summaries and another training example with the other summary. And so we can train and evaluate also the model if it can influence the summary towards a particular topic. So we evaluated the metric that we proposed with 62 graduate and undergraduate students. We gave them a summary in the topic, and we asked them to rate how similar it is to the topic from 1 to 10. And we see that we have a very nice correlation of the human evaluation with STAS. And with respect to the methods, we see that among the 3 methods, here we have Bayesian model, the pretending approach, this inspired from control sum works best, but if we combine pretending and tagging, this gives the best results, and also with respect to STAS. So we are trying to improve this idea and generalize it, and we have we revised this under second review now in natural language engineering. And the idea is to move away from a closed set of topics and be able to influence the summary towards any input document. It could be a few words, it could be a phrase, it could be a document, it could be a set of documents. Whatever it is, we compute a semantic representation through, for example, sentence transformers here, and we have a representation for the whole context. And for our document, we have the same representation for each word. So what we do now is we compute the similarity of the semantic representation of the words, the embeddings of the words, let's say, with the embeddings of the document, of the context, where we want to influence the summary, and we tag the words that are mostly similar according to these representations. So this basically generalizes our approach, and we can use a particular ground truth summary as context to train the model. So we see the similarity of the ground truth with the words here, and we tag the corresponding words. And another interesting thing that we see is that the rival models, like control sum, in their effort to influence the summary towards a particular topic, they hallucinate. So here there is an article about paleontology and dinosaurs and things like that. And we ask control sum to influence the summary of this document towards science and neuroscience. And it starts saying things that are related to this document, but then in the end it says it was published in the journal Science and Health. This is a hallucination just to in its effort to influence toward this topic. And the same here, it hallucinated something. While our approach with the tagging doesn't have this problem. Okay. And also we, in our results, in a data set now that has ground truth for topic, oriented summarization, we also compared with LLMs, and we found that our approach is quite well in the standard metrics, but also we suggested a new metric again to take into account to penalize hallucinations. So you can see that some models, for example, like Claude and control sum, have hyposign similarity of the produced summaries with the topic, but the corresponding rel metric that we introduced is lower than us. And the reason it is lower is that we penalize it for hallucinating things that are related with the topic, but unrelated with the topic. So we hope we have an accepted decision on this one. So I don't have enough time, but maybe just to give you a quick idea. So this was just a simple adaptation of an existing model to financial data. But the results were quite interesting in terms of publicity, at least because the CEO of Hugging Face said about our model, that a new model for financial summarization. Also, there were some posts that it works better than the authors, the titles of the summaries of the authors themselves. And we are quite popular in Hugging Face as well. We are among the top 20 models, among models from Google and Meta in summarization. And we are in the top 10 in likes. I don't know why. I don't tell my students to like the model just for this, but maybe I guess many people are working in the finance sector, as you may understand. And we have also made some comparisons that, at least with zero shot ChatGPT, if we compare it, our model fares better. And another interesting application is about trying to bridge the gap between the complex language of scientists in clinical studies and scientific publications and patients, on the other hand, and general audience. And there are surveys that request scientists to speak in simpler words, but there are also regulations. So to address this, we recently published a dataset and approach to try to summarize clinical trials. And maybe I just can skip to this slide where we see that there are some issues, especially with numbers, because medical documents like clinical trials have a lot of numbers. 10% of the patients had adverse effects, okay, for example, and things like that. And the models don't do very well in this. And this is something we want to address in future research. We have also like typos, and we have also hallucinations. And also we participated and received the 7th position out of 57 participants in a recent, in August, challenge about summarizing scientific articles. And here what we did is we also introduced a new dataset from this Science Journal for Kids resource, where it has scientific articles written in plain language just for kids. So by also acquiring this data, we managed to achieve interesting results. So as I don't have more time, just like to move on to the summary. So we discussed about neural abstractive summarization, and mainly I had time to tell you about how to compute and take advantage of uncertainty in terms of active learning and how to control the topic. And we saw quickly some applications. So I'd like to also thank my team, 2 PhD students on this topic that are finishing this year, and several other undergraduate students and colleagues at the company. So thank you very much, and I'm open for questions.
I can maybe start. Thanks, great presentation, and there's actually quite a bit that I'd like to discuss with you more later. Do you have this uncertainty estimation in the first part of the presentation? Do you have any intuition about what kind of documents typically are uncertain? Like, are there some characteristics or features in those documents that typically end up having lots of uncertainty in their summaries?
Yes, good question. As I said, one type, unfortunately, of documents is those that are out of the distribution, so like more outliers, so there might be noise in some data sets. So this could also be used for cleaning, for example, the data. But we haven't looked at the properties of other kind of what is being really selected. I guess it should be different documents than the documents you already have, in a sense. But this is captured also from the similarity metric in any case. So it should be, on the other hand, it should be difficult to predict correctly. But this is a good idea that maybe we could explore. Thanks.
Maybe I can ask. How are you? Maybe I missed it, but in the same first one that you talked about, how are you computing the uncertainty?
Okay, so what we do to compute the uncertainty is that we take the document, we pass it through the model, but we do this multiple times, let's say 10. And each time we have a different dropout mask, so we get a different summary. So in the end, we have 10 summaries. And then we measure the variance of the summaries. And this variance is based on the overlap of word engrams, let's say, among the summaries.
Okay. So what's the Bayesian part there?
The Bayesian part is inherited from the work on Monte Carlo, because this is like a Monte Carlo dropout. This is supposed to approximate. Yes, Bayesian.
Yeah, that was the kind of
yes.
Wondering. Like,
this is like approximating the full Bayesian interface.
Sorry, maybe I missed it, or maybe my knowledge is not that good. But I wanted to ask, you talk a lot about topic embeddings, and I was wondering if you had any ideas on if you wanted to reorder. The summarizations typically happen chronologically, like you have the document, and you get a summary is chronological. If there's a way to then cluster parts of it or rearrange them.
All right. Thank you for the question. So, no, it's very interesting. So, first of all, a comment on the chronological aspect that you mentioned. So, in these models, the encoder will read, let's say, the document, the whole document, and if it fits, but this is a different topic. And now the contexts are bigger anyway, these models, with techniques like sparse attention. So it processes the input document, it learns a representation from this document, and then we have the decoder producing the abstractive summary. It doesn't necessarily mean that it will follow the order of the document. Maybe the same things, for example, are discussed in the beginning and in the end. So it will not repeat, hopefully, this work. It will learn to abstract and to do this kind of clustering. Uh,
I'm thinking in the context of instructions or something where there is like a prerequisite. The text is not necessarily given in that.
yes. So then we could apply some kind of post-processing, try to identify the coherent parts, let's say, of the summary, and then maybe ask the user if he wants to, if they want to change the order. But yes, I have not worked on something like this, but it's interesting.
Maybe if somebody has any question online, they can unmute themselves and ask. In the meantime, you can.
I can maybe ask about this topic tags that you had. So they are trainable. How do you exactly train those? And maybe in many space.
Okay, so the approach with the tagging, it's not exactly trainable. Let's consider perhaps this, because this is, I like more this more recent work that we are trying to publish because it's more generic. So here we don't learn any embeddings for the tags. We use pre-trained models to map the context document where we want to influence. This is like the topic. It would be just a phrase discussing the topic, science and agriculture, whatever. It could be a document, it could be a paragraph, it could be a set of documents. So using pre-trained models like Sanders-Bert that are specifically trained for similarity tasks like information retrieval. So they compute embeddings that are good in computing similarities. That's why we do. We have the embedding of the topic, and then we pass from the same model each word. We have the embedding, so this is the word, this is the word, this is another word. It's all the words in our document. So then we compute the similarity of topic in the same space, in the same semantic space, with each word. And if we find a word that is similar to our topic, we tag it. Okay, so this is the idea. So if it is above the threshold, or we would say I want the 10% highest words to tag. We can do this during training using these concepts, using the ground summaries context. We can do this, and then the model we learn implicitly that whenever it sees this token, it should pay attention to this, because these words are very similar with this. So then during inference, we can tag whatever we want. We can tag any word. And hopefully the summary will be influenced towards the semantics of these words. So it's quite, I like it because it's quite flexible. Personally.
So during inference time, let's say you have an article about Barack Obama, and now you want to create a summary that focuses on, I don't know, what would it focus on? Well, obviously politics. So then would you then somehow process this article by adding these politics tags?
We could have a user tagging words, so like clicking words to tag them. So we could also have a UI for this to make it like for humans, or the human would give a collection of documents, and we then would compute the embeddings of this context, then compute the similarities with the document, and automatically propose them these tags. And the user might say, okay, or I want to delete something. So this, I personally like very much this idea. At some point, we were considering whether to even to patent it, because imagine someone watching news articles, for example, and building a context, then having this context and computing this, then we could influence the summary of a new article based on his interests with this very, very flexible way. So I hope the reviewers also are satisfied with the revisions and accept.
Maybe just nobody else has a question. I'm still stuck on the uncertainty part.
Yes.
You said, so how are sensitive are the results to the dropout rate, or are they do not really check it out?
So this is something we have not really investigated. So we use some standard about parameters. I'm not sure we investigated this in depth. But it's a good point. Maybe if we tune this, maybe we will get better results.
Yeah.
So good idea. Thanks. Although this is a more or less. Oh, we are still working. So okay, we can look at.
Yeah.
So instead of blue here, can we use?
Yes, I guess we could use other too because Roku is also based on word engrams. But we saw that this was being used, for example, in machine translation, so that's why we use this. I don't think we explored many alternatives here, so that's another idea. But I think that in this work, really the problem is how to deal with the outlier selection. Maybe this idea that was raised before helps.
Okay, we can end the discussion now. So let's thank the speaker again.